Continuous charge distribution. In practice, we deal with the charges much greater in magnitude than the charge on an electron. So we ignore the quantum nature of charges and imagine that charges is distributed in a region in a continuous manner. There are three types of continuous charge distribution. First one, line charge distribution, in which the charge is distributed over length of a conductor. In this diagram, we see that the total charge Q is distributed over length L and a line element delta L on which charge is distributed is what? Delta Q. So, line charge distribution, it is a charge distribution along a line in space. The linear charge density lambda is defined as at any point on this line as charge per unit length at that point. That is lambda equal to delta Q upon delta L. SI unit of lambda equal to coulomb per meter. Delta Q equal to lambda delta L. If total charge Q is distributed over length L, then lambda equal to Q upon L or Q equal to lambda L. Dimensional formula of lambda equal to m0 L minus 1 T1 A1. Second, surface charge distribution. Here we have a plane surface on which total charge is distributed. Q distributed over surface area S. Here we take a small area element delta S on which charge is distributed is delta Q. It is a charge distribution spread over a two-dimensional surface S in the space. The surface charge density at any point on this surface as charge per unit area at that point. That is sigma. Sigma is what? Surface charge density equal to delta Q upon delta S. So SI unit of sigma equal to coulomb per meter square. Dimensional formula of surface charge density equal to m0 L minus 2 T1 A1. So delta Q equal to sigma delta S if total charge Q is distributed over area S, then sigma equal to Q upon S. This implies that Q equal to sigma S. Volume charge distribution, it is a charge distribution spread over 3D volume of space. The volume charge density rho at any point in the volume as the charge content per unit volume at that point. Here we see one volume is available in which a charge Q is distributed over volume V. Here we take a small element delta V on which charge is distributed is what? Delta Q. So volume charge density defined as delta Q upon delta V. So SI unit of volume charge density is coulomb per meter cube. Dimensional formula of volume charge density is m0 L minus 3 T1 A1. So from this relation we get delta Q equal to rho delta V. If total charge Q is distributed over volume V, then rho equal to Q upon V or Q equal to rho V. Electric field due to a point charge at r distance is given as E vector equal to 1 upon 4 pi epsilon 0 Q upon r square r cap. For continuous charge distribution in line charge distribution, Q equal to integral lambda dl. In volume charge density, Q equal to integral rho dV. In surface charge density, Q equal to sigma ds. Now electric field due to a line charge distribution at r distance, E equal to 1 upon 4 pi epsilon 0 integration lambda delta L r square r cap. Electric field due to a surface charge density at r distance, E equal to 1 upon 4 pi epsilon 0 integration sigma ds upon r square r cap. Electric field due to a volume charge distribution at r distance, E equal to 1 upon 4 pi epsilon 0 integral of rho dV upon r square r cap. Gauss law, very important. According to this law, the total electric flux phi through a closed surface is 1 upon epsilon 0 times the net charge enclosed by the closed charge. Phi equal to E dot ds, integration of E dot ds equal to 1 upon epsilon 0 time into Q, or phi equal to Q upon epsilon 0. In other words, the total electric flux phi through a closed surface is equal to the ratio of total charge enclosed by surface to epsilon naught. Proof. Derivation of Gauss law from Coulomb's law. We consider a point charge Q. We assume that the surface S is a sphere of radius r centered on Q. Electric field at any point on S is given as E equal to 1 upon 4 pi epsilon 0 Q upon r square r cap. So here one charge Q is centered at the center of the sphere, and we want to find the electric field at point which is at distance r from this center. Electric flux through this area delta S equal to delta phi equal to E dot delta S, as E and delta S are in the same direction, so delta phi equal to E delta S cos phi, delta phi equal to E delta S. Here we can see that E and delta S are in the same direction. Total electric flux phi equal to integral of delta phi equal to E delta S, phi equal to E taken as a common integral of delta S. So phi equal to, we just put the value of E as 1 upon 4 pi epsilon 0 Q upon r square integration of delta S. Integration of delta S is total surface area of the sphere, which is 4 pi r square. So phi equal to 1 upon 4 pi epsilon 0 Q upon r square into integration of delta S as 4 pi r square, 4 pi cancel, r square cancel, so we get phi equal to Q upon epsilon naught. This proves Gauss law. Now next one, Gaussian surface. Any imaginary closed surface enclosing a charge is called the Gaussian surface. We can easily find the electric field produced by certain symmetric charge configuration. Calculation of flux of uniform electric field through the surface of a cylinder. Here we can see a closed cylindrical surface in flux through entire cylinder phi equal to integration of E dot ds at 2 E dot ds and third at E dot ds. At one surface, the angle between E and ds is 180, at 2 angle between E and ds is 90 degree, and at 3 angle between E and ds is 0 degree. So phi equal to EDS cos 180, EDS cos 90 degree, EDS cos 0 degree. So we just substitute the value of cos 180 equal to -1, cos 90 equal to 0, and cos 0 equal to 1. On solving, we get phi equal to minus E integration of ds plus E ds, and this value tends to 0. So phi equal to minus Es plus Es equal to 0. The total flux is 0. We find that the net electric flux through a closed surface is 0. We conclude that the total charge contained in closed surface is 0. Important points about Gauss law. First one, it is true for any closed surface. It does not depend on shape and size of the closed surface. Second one, it depends only on the charge enclosed by the closed surface, irrespective position of the charge inside the closed surface. Third, the point on which we want to find the electric field by this law must be present on the Gaussian surface. Fourth one, the Gaussian surface must be symmetric, so we get much easier calculation of electric field. Thank you.